Welcome to Algebra 2. Today we've got section 1.4, day 2. Yesterday we talked about solving two variable linear systems of equations, and today we're moving on into three variable linear systems of equations. Let's take a look at some of the differences. So a linear equation in three variables follows the format. We've got something x, something y, something z equals a constant. So z is our third variable that we're dealing with. And it's still a linear function because we've got terms that are not raised to powers. There's no square roots. There's nothing fancy there, right? They're all first power terms called linear terms. A system of three linear equations. Okay, right? If we're going to have three variables, we have to have three equations in order to solve. The answer is in the form of an ordered triple, x, y, and z. So we have three unknowns, three variables. Our answer is going to contain three solutions, or three parts to the solution. While they are equations of lines, graphically, these equations that have an x, a y, and a z, they represent planes in three-dimensional space. So no longer are we working on a flat plane with just two lines being drawn, but now we're working in three-dimensional space with planes being drawn. Okay, just like before, we've got three different types of solutions. First of all, and most commonly, there's exactly one solution. So those three planes that are intersecting in space intersect at one point, the point x, y, z. Infinitely many solutions, the planes may perfectly overlap, or they may intersect in a way kind of like this paddle wheel looking diagram off to the right. You can see they intersect to make a line. So there are infinitely many points of intersection there. And again, we'll find infinitely many solutions when, in using our algebra, we end up with 0 equals 0. And lastly, we may have planes in space that are intersecting in ways such that no configuration of them has all three planes meeting at a single point or more. That's our no solutions case. You can see visually what those might be representing in three-dimensional space. Again, this is where we have 0 equaling a number. So again, not always going to be 7, but some number, some untrue statement with no variables left. All right, with three variables comes a little bit more complexity. So our steps to solving, and these are just guidelines, and you'll get the feel of these, solving these types of problems as we move along, but it's kind of like a two-tiered elimination. Okay, so the first thing we're going to try and do is rewrite this system as a system of two equations using, it says substitution or elimination. I would strongly encourage you to use elimination. Sometimes substitution works, but I would strongly encourage elimination. Our goal is to use all three of the given equations to produce two equations that have the same two variables left over. Okay, and after that, steps 2 and 3, we're going to solve the new system to find both of its variables, and then we're going to substitute those variables back into an original equation to find the third variable. Okay, and after our steps, you see it says note, this is how to tell as a result of our algebra, how do we know if we have no solutions or infinitely many? So that's what those are there to provide. So let's take a look. Our first example, you can see that we've got three equations, and this last equation, check this out. The last equation has 0 y's in it. All right, well, I just need to involve all three equations, and my goal is to get to a point where I've got two equations with two unknowns. And because there's 0 y in this third equation, it's already got two unknowns in it. There's no y. So what I want to do is I want to take these two and eliminate y so that I have another equation that has just x's and z's in it. And if we take a look at this, I'm going to write this work off to the side because a lot of issues occur just by not being organized. I'm going to rewrite this elimination problem that I'm going to do with the top two equations because as I take a closer look at it, it's already set up to perfectly eliminate the y's. Okay, so I'm good to combine like terms. I've got negative 3x, I've got no y, I've got plus 2z equals 3, and then I always like to put a box around my equations when they have two unknowns in them. So this one had it from the start. Let's put a box around that one as well. So what we've just set up for ourselves are two equations with two unknowns, and we've involved the first two equations of our system. Now, when I go about solving these two equations that have two unknowns in them, if I set those up, now I'm going to bring that third equation from the original problem into play. 2z equals 3, negative x minus 2z equals negative 7. And I just want to look at those two and say, hey, is there an easy elimination that I could carry out here? And sure enough, the z's will eliminate rather quickly. I don't have to make any adjustments. So let's go ahead and combine. I get negative 4x, my z's cancel out, and I have that equal to negative 4. If I divide both sides by negative 4, now I'm getting somewhere. X equals positive 1. And I just kind of put a little circle around that. I'm going to need that. Once I've found my first variable, it's just a matter of working our way backwards now and substituting in what we now know. So I know x equals 1. I'm going to go back to one of my two boxed equations from earlier and substitute in that x. This will help me find z. So negative x is negative 1 minus 2z equals negative 7. Let's add 1 to both sides. Divide by negative 2. I find that z equals 3. And now what I'm going to do is, I know that x equals 1, and I know that z equals 3. I need to solve y. Let's go back and substitute those two known values into one of the original. Go all the way back to the start, and I'll be able to finally solve for y. All right, so I'm going to use that middle equation that I was given because it looks like the easiest one to work with. Any one of those top two will work. So I've got negative x, and I know x is 1, minus 4y, don't know that yet, plus 3 times z, that's 3 times 3, equals 12. And if I solve this for y, I've got the problem knocked out. All right, I'm going to combine like terms, subtract 8 from both sides, divide both sides by negative 4, and I get y equals negative 1. Now I can bring everything together into my final solution. 1, comma, negative 1, comma, 3. There's my ordered triple solution to that problem. And I know it seems like a lot. And this may be something that now that you've copied everything down, you want to go back and just, rewind a little bit on this YouTube video. Go back and watch the process again. Just kind of watch what was carried out, because once you know the steps and you're able to keep your work organized, these problems are not difficult. They're just a little time consuming because there's so much writing. And as a little insider tip, it's also really nice if you use the formatting of boxing your equations that have two variables and kind of circling your solutions as you find them. It makes them much, much easier for me to grade too, which can be a big benefit to you. All right, let's keep going. All right, so directions simply say solve the system. Now, before I begin, the other one, the previous example that we just did, was pretty easy because we already had one equation that had only two variables in it. Well, what if I start off with an equation that has all three variables in all three equations? And this is pretty likely to occur. I just want to look at the entire problem and make a decision. Which variable looks like the easiest one across all three equations to cancel out? I want to try and have the easiest run through the elimination method that I possibly can. And it looks like the x's are going to be the way to do that. They have the smallest coefficients. So I want to find a way to eliminate the x's using all three equations. So I'm going to start by grabbing equation 1 and equation 2. I'm just going to mark it like this. Again, I want to stay organized. And in order to get the x's to eliminate, I'm going to have to multiply the top equation by a positive 2. Now, working with those two, I have negative 2x plus 4y minus 4z equals negative 30. And then the second equation, I'm leaving that one alone. 2x minus 5y plus 4z equals 22. Okay, this will lead me to one of those boxed equations that has only two variables in it. Well, let's see what happens. My x's cancel out, and I have negative 1y. Ooh, and my z's cancel out as well, and I have negative 8 for a constant. This is a really good thing as well, because if I divide both sides by negative 1, I very quickly get that y equals a positive 8. So I skipped right over that equation that has two variables in it, and I know one of my one of the pieces of my solution right now. Okay, well, step 2 was to incorporate the last equation, and again, I want to eliminate the x's. So I'm going to grab equations 2 and 3 right now, but I need to make an adjustment if I'm going to have elimination happen. I'm going to multiply this equation by negative 1. I'll then have negative 2x plus 5y minus 4z equals negative 22. And that last equation is not going to be changed. 2x minus 2y plus 4z equals negative 16. Okay, well, if we carry out this elimination, combine all the like terms together, again, my x's and my z's cancel out. I have 3y equals negative 48. And now if I divide both sides by 3, I find that y equals negative 16. Huh, that doesn't seem right. How can I get y to become two different things? Weird. Weird, weird, weird. Something fishy is going on here. Let's take a look at what would happen if, let's say I go back and substitute in the values of y equals, let's use y equals 8. Let's say that once I find that, I go back and I say, what are the two easiest equations to plug y into? The first and the third. Well, then I would have negative x plus 2y is 16 minus 2z equals negative 15. And then that third equation, I would have 2x and then negative 2y, which is negative 16, plus 4z equals negative 16. And if I combine my like terms here, oh, it's not set to eliminate just yet. Hold on. In the top equation, if I subtract 16 from both sides, and in the bottom equation, if I add 16 to both sides, I'm just trying to set up an equation that has two unknowns in it. So negative x minus 2z equals negative 31, and then 2x plus 4z equals 0. Well, let's try and work with this. And again, we're just kind of tabling all that work in blue for now. I've incorporated all three equations. I used the first two to find y equals 8, and I brought in the third equation right here. Let's see what happens. In order to eliminate the x's, let's say we're going after that next. Well, then I would have to multiply the top equation by 2. So then if I rewrite it underneath, I would have negative 2x minus 4z equals positive 31. Ah, that's why we were getting that weird result. When I eliminate, my x's and my y's eliminate, and I end up with 0 equals 31. This is a no solutions situation. So what can we take away from this example? Well, that work in blue was all extra writing that we really didn't have to do. So if we go through and we start our three variable system and we happen to get a lucky break like this and we get a variable solved for right away, substitute that back in immediately and then involve the other equation. So in this case, we substituted it back in and we involved the third equation, which we hadn't used yet. That way we can get to our answer of no solutions without doing any work off to the side. All right. Next, let's have a look at this one. Here it looks like, yet again, the x's are going to be probably the easiest one to handle. But since we've already done the x's, trying to eliminate those, let's work with the y variable instead. So if I grab the first two equations and I want to eliminate the y's, I'm going to have to multiply that top equation by 3 to set up that cancellation. Okay, I will then have the system of two equations, 6x plus 3y minus 6z equals 45. And that second equation, I didn't change that, trying to cancel out the y's. Oh, and this looks kind of similar to what we had before. Let's see if we can't put that to practice. I find that 8x equals 24 and x equals 3. And since I've got this value of 3 right away, I'm going to start substituting that back in. Which ones look easiest to work with? Well, I haven't used the third equation yet, so I have to plug it in there. And I'm going to choose that first equation again. So now I have 2x, which is 6, plus y, minus 2z equals 15, just plugging in that value of 3. And in the bottom equation,
Mr. Stuckey, please report to the attendance office. Mr. Stuckey, please report to the attendance office.
I apologize for that interruption. The bottom equation, when I plug in that value of 3, I get negative 3 minus 3y plus 6z equals negative 30. And I want to get this set up as an equation or a system of equations that just has y's and z's in it. So I'll subtract 6 from both sides in the top, and I'll add 3 to both sides in the bottom equation there. Y minus 2z equals 9, and negative 3y plus 6z equals negative 27. And then if I want to eliminate, let's say I want to eliminate the y's again. I'm going to choose to divide this bottom equation by 3. I'm allowed to do that. Then what I set up is a top equation that's y minus 2z equals 9, and a bottom equation that's negative y plus 2z equals negative 9. And if I try and eliminate here, solve for one of those other variables that I don't have yet, I find that my y's cancel, my z's cancel, and my constants cancel. This is an infinitely many solutions situation. Infinitely many solutions. Those planes intersect in a way where either the planes perfectly overlap each other, or, as we saw in the visual on our second or third slide, they're intersecting to make a line that has infinitely many points on it. Moral of the story, though, if we get to 0 equals 0, we have infinitely many solutions. Now, just like with two variable systems, these are very useful in finding unknown information in the real world. So here we've got an ad for a furniture store that has different combinations of furniture for different prices. And using this information that's given in their little advertisement, we can find out how much each piece of furniture costs. Just like before, we want to RTQ, read the question, what are we trying to find? Let's set up some variables so that we know exactly what we're solving for. I'm trying to find the cost of a sofa. So S equals cost for the sofa. I want to find the chair. So C equals the cost of a chair. And then L equals the cost of the love seat. Okay, and we've all heard ads like this on the radio before, but this is kind of cool that we could sit down and actually figure out what each piece of furniture is based on some different combinations. All right, so I'm trying to find costs. I'm trying to find prices. That's what my variables mean, the cost of each piece. Let's look at the advertisement, $1,300 for a sofa and a love seat. So as I'm setting up my system, I want to turn that into a math equation. The one sofa and one love seat is $1,300. Then next, one sofa and two chairs is $1,400. And lastly, a sofa and a love seat and one chair is $1,600. All right. And this is actually really helpful because you can see that we've got a couple of equations that already have two variables in them. So that's good. We just need to pick one. We need to organize our work here. And I'm going to choose to keep this top one. S plus L equals 1,300. That means I want to take these two equations and use the elimination method so that I get another equation that has just S and L in it. So in other words, I want to eliminate C. To make that happen, I need to multiply this bottom equation by -2. And here's what I'll get as a result. My top equation did not change. S plus 2C equals 1,400. Now my bottom equation becomes -2S minus 2L minus 2C equals -3,200. And although it looks really complicated, it looks like we made it more difficult, this will actually produce something that we can work with. So keeping it organized shows us that we're on the right track here. So let's combine our like terms. I've got S and -2S. I've got no L's and -2L. I've got 2C and -2C. Those cancel just like we wanted. And if I combine the constants together, I get -1,800. So I'm going to put a box around that. That has S's and L's in it. And I'm going to put a box around the only one of the originals I haven't used yet. That has S's and L's in it. If I take those boxed equations, again, I'm keeping everything organized, and I set those up as a two-variable system, I should be able to use the elimination method again. Oh, and look at that. It's already set up beautifully to eliminate the S's. So I get -L equals -500 when I combine the like terms. That means L equals 500. Again, I'm going to hang on to that value. Then what I want to do is start working my way back. So go back to one of the boxed equations. I'm going to choose this one. Since I know L, I know that S plus 500 equals 1,300. Subtract 500 from both sides, S equals 800. All right, now I want to look at all the equations that I've kind of set up along the way, and I'm trying to say to myself, I know S, I know L, what's going to be the easiest way to solve for C? So we could take this S equals 800, and we could just plug that into equation 2. That looks pretty easy to do. Or we could take the L and the S and plug both of those into equation 3. Either way, we're going to get the same answer. So I'm going to choose the one that involves that middle equation in blue, and I'm just going to plug my S value of 800 in. 800 plus 2C. C is the only variable I don't know yet. That equals 1,400. Subtract over the 800, 2C equals 600. Divide both sides by 2, C equals 300. All right, so we did it. I want to be sure that we answer the question. So the sofa, we said that was $800. Be sure that we're labeling that. There's part of our answer. The chair was $300, answering that with units, dollars, right? And then the love seat was $500. And just to see if that makes sense, let's kind of run through these with some mental math, plug them back into our advertisement there. A sofa and a love seat. Does that add up to 1,300? Of course it does. It's 800 and 500. Does a sofa and two chairs add up to 1,400? 800 plus two 300s, yes, that makes $1,400. And a sofa, a chair, and a love seat, if I add all three of those together, do I get $1,600? Yes, I do. So the work we did solved the problem. Okay, and our final example for three variable systems, tying in a little bit of geometry. This is a great indication of what you may see on like an SAT test or something like that, something that combines algebra and geometry. Those problems seem pretty common considering the SAT problems that I have looked at. So the question simply says, it's number 34 out of your textbook if you're interested, what are the measures of angles A, B, and C? Okay, so I'm trying to find the measure of angle A, the measure of angle B, and the measure of angle C. Let's take a look at this diagram and see what we can piece together, what we know about this situation. Okay, first of all, up here in the top it says that angle A equals A degrees. That is not going to tell us anything, so we don't get anything out of that angle of the triangle. Down here at angle B, they're saying that angle B equals 5A minus C degrees. Okay, let's write that out. The measure of angle B, and I'm just going to use a variable for now, is equal to 5A minus C. And then over here in the corner, it looks like a right angle, but I'm not going to assume that it is. It says that angle C is equal to A plus B. Well, if we combine that with what we had up above in the top angle, A equals A, we don't have enough information, right? Because we have three unknowns, I need three equations. So I want you to think for a second, what do I know from geometry that deals with three angles of a triangle? And hopefully we don't sit too long before we remember, oh yeah, if I have A and B and C, those angles must sum up to 180 degrees. There's our third equation. That's what we needed to solve this three equation system. Now, what I'm about to show you is in no way the only method of solving this problem. It just ties in with how we've organized them in the past. You can use some clever substitution and elimination tricks that involve all three of these equations and get the correct answer maybe faster than what I'm about to show you. But I think that the more we can tie this into a procedure that we follow, the more we're going to understand the concept. So the first thing I'm going to do is rewrite these equations in the familiar format that we have, where our variables go in order, and then they're equal to some number. So if I have 5a and I subtract the b from both sides, I get the equation 5a minus b minus c equals 0. Notice how the variables go in order, and it's equal to a constant on the right. For the second equation, I'm just going to subtract c from both sides. That's telling me that a plus b minus c equals 0. Now I've got three equations with three unknowns in them, and they're all set up in that really nice format that we wanted from before. And in looking at these, I noticed that it looks like the b variable is going to be pretty easy to cancel out. So my first task, I'm going to combine these first two equations in blue because b is already set up to eliminate there. So I've got 5a minus b minus c equals 0, and a plus b minus c equals 0. If I combine my like terms, that's 6a minus 2c equals 0, and I'm going to box that one up. That's an equation that now has two unknowns in it. And now in green, I'm going to take equation 1 and equation 3 because those are also set up to eliminate the b variable. I have dodged a little bit of extra work that way. So first equation, I know it's extra writing, but it's going to keep everything really, really organized. All right. Whoa, look at what's going to happen here. If I carry out my elimination method, I'm just trying to eliminate the b's, but I find that 6a equals 180. The c's also canceled out. If I divide both sides by 6, I find that a equals 30. And we are really, really lucky right now because, first of all, we've used all three equations. Secondly, I got an equation that has two variables in it. And then right away, I was able to find one of the variables. So I'm saving a step right here. Now we know one of the variables. Let's work our way back. I'm going to plug a into this boxed equation that I have. So 6 times a minus 2 times c equals 0. Well, 6 times a is 180 minus 2c equals 0. If I subtract 180 from both sides and then divide by negative 2, I find that c equals 90. So now I know 2 of those variables. And I'm able to take those and plug them back into any of the 3 original equations that I had set up here. And I'm just going to choose, let's see, what color haven't I used in a while? Blue. I'm going to choose to plug both a and c into the 3rd equation. It doesn't have any negatives. It just overall looks easiest to work with. So I've got a, which is 30, plus b that I don't know yet, plus c, which is 90, adding up to 180. If I combine like terms on the left and subtract both sides, subtract 120 from both sides, I find that b equals 60. And I know some of you that, coming fresh out of geometry, you probably look at that and you're like, oh, I know as soon as I get 30 and as soon as I get 90, I know the other one has to be 60. It is a special right triangle. So you would be correct there as well, probably using the same math we wrote over there on the right in blue. Let's answer the question. The measure of angle A is 30 degrees. Measure of angle B, 60 degrees. And the measure of angle C, it did end up being a perfect right angle, 90 degrees. There is our solution. Now, I realize this was a longer video and that some of these procedures take a while to write out. I cannot stress enough the importance of taking the time and keeping yourself organized. A little bit of time spent writing is well spent when you consider how much time you would spend trying to piece together all your work, and maybe you lose a negative or something. Keep this work organized. It's not difficult, it's just tedious. That does it for day 2 here of section 1.4 in Algebra 2. Your assignment, it's another worksheet, not as many problems, obviously, because these take a while. But again, give yourself the practice, mainly in keeping yourself organized. Hope you've enjoyed this lesson.